Hello. Today's video lecture will give you an aid to how to prove the famous Cauchy's integral formula. Cauchy's integral formula is one among the essential facts of complex analysis, especially in complex integration. So the statement of the formula says that we are given with a function f from G, open connected set G, to the complex plane and it is analytic. And suppose BAR closure, which is the closed disk having A as a center and R as the radius, is contained in this G such that the radius R is strictly greater than 0. And we are given a curve which is gamma of t defined as a plus r e raised to it, where t is varying from 0 to 2 pi. Then for every z that happens to be in modulus of z minus a strictly less than r, that means an open ball centered at a with radius r, every point inside that disk, we can say that f of z is equal to 1 by 2 pi I integral over gamma f of w divided by w minus z dw. So for a convenience to prove, we are assuming that a is equal to 0 and r is equal to 1. That's what we see in the first paragraph of the proof. So suppose if we are not assuming like that, then what we have to take is that we have to define a function g of z is equal to f of a plus rz, and g1, capital G1 is equal to set of all points of the form 1 by r into set minus a, where set belongs to g. So if we assume a is equal to 0 and r is equal to 1, by considering the above facts, we can reach the conclusion. So that's how we start. So now we are moving on, assuming that a is equal to 0 and r is equal to 1. That means this b bar of ar is nothing but b bar of 0, 1. Okay. So this will be modulus of z minus 0 strictly less than 1. That is modulus of z strictly less than 1. And also gamma of t is nothing but 0 plus 1 into e raised to it, which is equal to e raised to it. That is gamma of t is equal to e raised to it. Okay. So let's see how we can rewrite what we have to obtain. Okay, so we are fixing a z such that that z is inside this open disk, which is nothing but now modulus of z strictly less than 1, as a is 0 and r is 1. Now what we have to show, we have to show that f of z is equal to this, right? So we have to show this f of z is equal to 1 by 2 pi I integral over gamma f of w divided by w minus z dw. And here we have w to be equal to gamma of s. We are using the definition of line integrals here because we know what gamma is according to its parameter here and the variation of the parameter. So you can write the lower limit and the upper limit of that parameter 0 to 2 pi. Instead of w, we have gamma of s. We are taking it different from s as we are taking it as s instead of t because you already have an s for the substitution there. So we are just making a little change there. Okay, so we have gamma of t is equal to e raised to it. That means w is equal to gamma of s, which is equal to e raised to is. dw is equal to d of e raised to is. That makes us understand that s is the variable there. So you get I e raised to is ds. So substitute all those in this line integral. You get 1 by 2 pi I integral from 0 to 2 pi f of e raised to is. Instead of w, you have e raised to is right here. and instead of dw you have I e raised to is ds. So you have an I here. Along with this, you have an I here, okay, and also you have an I here in the equation. So you can cancel out that I and the I in the numerator. Okay, so you are left with this 1 by 2 pi I 1 by 2 pi integral from 0 to 2 pi f of e raised to is into e raised to is divided by e raised to is minus z ds. So in the next step, we are saying that we have to show that we are taking everything to the right. So you get 0 is equal to integral from 0 to 2 pi f of e raised to is into e raised to is divided by e raised to is minus z ds minus what you have 2 pi into f of z. We just rearrange. And I am trying to take this into the integral. For that, what we are going to do is minus, you are writing instead of this, you are writing integral from 0 to 2 pi f of z into ds, because f of z can be taken out. Ds, when integrated, you get s, and applying the limits you get 2 pi minus 0, so you are left with 2 pi into f of z. So you can rewrite it like this, and then you are taking the integral out with because of the property of the integrals, that is equal to integral from 0 to 2 pi f of e raised to is into e raised to is divided by e raised to is minus z minus f of z ds. Now our aim is to apply Leibniz rule as we proved in the earlier video lecture. So here we are going to define a function which is nothing but phi of st is equal to capital small f of z plus t into e raised to is minus z into e raised to is divided by e raised to is minus z minus f of z. Okay. So so there is a slight variation over the function. So instead of this e raised to is, there is a slight variation. Instead of e raised to is coming here, we are taking it to be z plus t into e raised to is minus z. Okay. Here t is varying from 0 to 1 and s is varying from 0 to 2 pi. And we know that we are defining the function for all z such that modulus of z is strictly less than 1. So you have to make sure that the function which we defined just now is well defined. That is f of this thing, right? That should be inside modulus of z strictly less than 1. So you have to check for that. So you are checking for this term z plus t into e raised to is minus z, take its modulus. Okay, that is equal to modulus of z into 1 minus t. You can rearrange it like that, plus t e raised to is. Okay, less than or equal to, using the modulus property, triangle inequality, less than or equal to modulus of z into 1 minus t plus modulus of t into e raised to is. That is less than or equal to modulus of z into 1 minus t plus modulus of t into modulus of e raised to is by the property of modulus. Modulus of e into e raised to 1 by s is equal to 1. Okay, and this is less than or equal to modulus of z. Okay, that is equal to. Okay, that is equal to, because modulus of z into modulus of z into 1 minus t can be written as modulus of z into modulus of 1 minus t. Okay. That is equal to modulus of z into modulus of 1 minus t plus modulus of t. And you know that modulus of z is strictly less than 1. So that means that is strictly less than 1 minus modulus of 1 minus t plus modulus of t. So here you have an observation to make. We know that 0 less than or equal to t less than or equal to 1. So from that you can infer that 0 less than or equal to 1 minus t is strictly less than, less than or equal to 1. So definitely this modulus of 1 minus t will always be positive, because of the fact that it happens to be inside 0 and 1. So this modulus sign can be taken out. So that is equal to 1 minus t. Also, t is also happening inside 0 and 1. So this modulus sign can be taken out. So you get 1 minus t plus t, which is equal to 1. So what you get is modulus of z plus t into e raised to is minus z is strictly less than 1. Right. That means the point inside this function is lying inside the open disk with center 0 and radius 1. Okay, so that means the whole function phi is well defined. Okay, and also it is continuously differentiable because our function is said to be analytic, right? F is analytic, and you have a combination of F and e raised to is coming here, right? And in the denominator, you have e raised to is minus z, and they will never be zero. Okay, so why they will be never be zero, because this z is coming from inside the unit circle and e raised to is will be on the boundary, so they will never coincide. So what you get in total is that this phi is continuously differentiable, or it is analytic. Okay, now we are going to define g of t is equal to integral from 0 to 2 pi phi of st ds. Okay, and by the Leibniz rule we know that this g is continuous, as well as it is having a derivative which is continuous. Okay, that is g has a continuous derivative since this phi is continuous. Okay, the next part is our we are aiming to prove that g of 0 is equal to 0. Okay, basic aim is to prove that g is a constant. So first we have to show that g of 0 is equal to 0. That is our aim. So we are going to compute it. G of 0 is equal to, by our definition, integral from 0 to 2 pi phi of s comma 0 ds. Okay, that is equal to, apply what is substitute what is phi of s comma 0. You get integral from 0 to 2 pi. Some elements go out, right, because this t is happening to be 0, so here this term will completely vanish. So you get f of z plus e raised to is divided by e raised to is minus z minus f of z. That is what we got here. Okay, and like we earlier did, we are going to integrate separately. So also you can take out this f of z outside the integrals, because we are integrating with respect to s. So you get f of z into integral from 0 to 2 pi e raised to is divided by e raised to is minus z minus integral from 0 to 2 pi ds. That will become 2 pi, right? So you get f of z into integral from 0 to 2 pi e raised to is divided by e raised to is minus z ds minus 2 pi into f of z. Okay, but earlier in the after we had proved the Leibniz rule from advanced calculus, we had proved that integral from 0 to 2 pi e raised to is divided by e raised to is minus z. That means this one. Okay, that is equal to 2 pi. We had proved it. So you get f of z into 2 pi minus 2 pi into f of z, that is equal to 0. Okay, so what you obtained now here is that g of 0 is equal to 0. Now we have to show that g is a constant. For that we are going to compute what is g dash. Okay, we know that by Leibniz rule g dash, if g of t is equal to, if g of t is happening to be like this, where this phi is continuously differentiable and so on, we know that, then g dash of t is equal to integral from 0 to 2 pi derivative of this phi. Okay, that's what we are going to do here. So you have, so g dash of t is equal to integral from 0 to 2 pi derivative of phi. We are calling the derivative of phi as p2 of st. Okay, for making it into a better understanding, we have phi of st is equal to the terms thing here. Okay, so dou phi by dou t will be equal to f dash of this quantity into e raised to is into the derivative of the term sitting inside, that is with respect to t, right? So you get e raised to is minus z, and the denominator, it will be a constant, so it will be there e raised to is minus z. You can cancel them out and to get this. So this is what they call as phi 2. Okay, phi 2 is equal to this. So what you get is phi2 of st, which is the derivative of phi with respect to t, is equal to e raised to is into f dash of z plus t into e raised to is minus z. That is an observation there. Okay, and also we have this t is varying from 0 to 1, and that suppose if capital phi of s is equal to 1 by it into f of z plus t e raised to is minus z, we are going to differentiate this function with respect to s. When we differentiate, you get 1 by it into f dash of z plus t into e raised to is minus z, okay, into the derivative of the term sitting inside with respect to s, that will be t into I into e raised to is. You can cancel out it and it here, so you get e raised to is into f dash of z plus t e raised to is minus z. Okay, that is nothing but equal to phi2 of st, which we mentioned now. Okay, phi2 of st, or you can call it dou phi by dou t. Okay. Now you can apply the Leibniz rule. Okay, no, you can apply the fundamental theorem, which says that g dash of t is equal to the capital phi of the upper limit minus capital phi of the lower limit. So we have to find capital phi of 2 pi. Capital phi of 2 pi is equal to substitute e raised to 2 pi. So you get e raised to I 2 pi, which is equal to 1, which is equal to 1, which will be, you know that e raised to 2 pi I and e raised to 0, that will be 1. Okay, so you get 1 by it into f of, so you get here to be f of z plus t into 1 minus z. Similarly here, f capital Phi of 0 will be equal to 1 by it into f of z plus t into 1 minus z. When we are subtracting, both are the same, so you get 0. That means g dash of t is equal to 0 for every t that is happening inside 0 and 1. So since this g dash is continuous, as we said earlier from the Leibniz rule from advanced calculus, you are getting that this g is a constant. So what was g of 0 before? We had obtained that g of 0 is equal to 0. That means this g is in total equal to 0. So that is how we end up with the theorem. So use the logic to finish out the proof rigorously. So thank you. you.